say.
So Michael Nielsen texts me, and he says, "Have you seen this?" And I had not seen this, and he sends me a link to this Henning Pauly video where he's talking about some new Marshall, and he's got it set up with an aux box and a power station, and he's talking about cranking a Marshall into a load.
Let me tell you a little story about this very fantastic Marshall modified 1959 M01. I killed it.
I think he's trying to convey some sense of...
well, he's taking the piss out of himself.
Kind of taking the piss out of himself. And
he's trying to do good looking out for the guitar community. Like,
he's saying, I don't really know what I'm talking about, but then he proceeds to sort of expound upon the stuff that he obviously doesn't know about, and not maliciously, just trying to convey some information that he's gotten from the people around him.
Sure.
And the only thing that he did wrong was he sort of misinterpreted it. And that caused like all these comments. Nielsen says, they're kind of demanding that you come in and respond. And I didn't really exactly see that, but like I said, I didn't read all the comments.
And this isn't in the spirit of having an argument. This is in a spirit of clarification.
Yeah, the way I understood it, do I understand it incorrectly? Blah, blah, blah. And I'm going, yeah, okay. How can we not add to that, but add some clarification at the same time?
Awesome. Okay.
And so here we are. This is going to be our attempt to kind of clarify everything and put some context around these concepts that people just seem to intrinsically get wrong. Bail Henning out, which, I actually do love Henning Pauly, and I do not like to see him taking abuse from people that probably don't know any more or less than he does. And that's going to be difficult because a lot of this stuff is things that people have been saying and believing for 30, 40, 50 years. I have here a PS2 sitting on top of a programmable power supply. And then we have a scope, and we have a signal generator, and we have a load resistor, and we have a fan, and we have a couple of RMS, true RMS reading digital multimeters. We have another multimeter that's set up to test temperature, and it's reading the temperature of the load resistor, and we have a PS100. Now, why do we have two power stations? Well, we use a PS2 to test all the power stations that we make. It's a test rig. It's a test tool, part of our QC process for testing PS2s, PS100s, PLIRs, and anything else that has a load. We use it for the ZMAX. So I've got everything all set up so that we can talk about this subject intelligently, I hope. All right. What's the statement that we want to approach first? The thing that started all this, sine wave power. What is sine wave power? For the sake of this discussion, sine wave power is essentially equivalent to RMS. So if you have a 100-watt RMS amp, it means that it's putting out sine wave power up to the point where the sine wave remains a sine wave. And that means that it's not clipping. And that means that the distortion inherent in the output signal is very, very low relative to what it would be like if you were way into the clipping range. How do we get from a 100-watt amp, the legendary 100-watt Marshall that puts out 150, 160, 170 watts on my bench? And partly because of electronic phenomena, partly because of ignoring how much distortion is actually being observed, and partly because improperly using the test tools that you're using. Okay, so let's start with the PS2. It's sitting up here idling, and we're going to turn it on. The power station down here is on bypass, so it's basically doing nothing except taking the output from the power station and feeding it into an 8 ohm load resistor, which is pretty cool right at the moment. It's a 108 degrees, 109 degrees Fahrenheit. The fan is not on right at the moment. I'm going to turn this on, and you see a little sine wave there. And this is the voltage threshold that we use for testing other power stations or other gear. Basically, this is sine wave power. The sine wave output gets converted to RMS power by reading the voltage, the sine voltage, the RMS voltage.
So this is an RMS meter.
This is an RMS meter, and it is reading this sine wave threshold or amplitude at 12 volts, RMS. What's that got to do with power output? You use an equation to convert RMS voltage to RMS power. Voltage, power, current, these are all related pieces of the energy puzzle. So we want to convert 12.5 volts RMS to how much power does that translate to RMS? And we do that by squaring the RMS voltage and dividing it by the impedance of the resistor that we're using as a load, which is 8. Okay, so to do that, we take 12.5, square it. In other words, multiply it times itself. Okay, so 12.5 volts squared is 156. Now we divide that by 8 ohms, and we get 20 watts. Like I said, this is the threshold, the output threshold that we use the power station for to test other power stations. We feed it 20 watts so we can make sure that everything is working properly. And then once we turn the unit on to drive its own load, then we check to see how much power it puts out. So right now, the PS2 is putting out 20 watts, and we're seeing the sine wave that represents 20 watts of sine wave power. Now, to get it to put out more power, we put more signal into it, just like you would when you're cranking an amplifier, and we keep turning it up until it flattens out a little bit, right here and here. This is the point of the onset of clipping. What is the onset of clipping? This is simply the power supply in the power station is at its limit. It's designed to put out X number of watts, and the power supply is designed to deliver enough current to the tubes and the output transformer to convert to the rated output, 40, 50 watts, whatever that may be. Once you reach that threshold, it starts clipping because the power supply can not deliver any more energy. And all that's left for it to do is keep shoving signal into the tubes that it can't turn into more power because they can't suck any more power out of the power supply to do that. So at the point of clipping here, now we're looking at 16 volts RMS. 1.6 times 1.6 divided by 8. Okay.
32.
Now we're at 32 watts. It's a PS2. It's a 50 watt power amp. Why is it only putting out 32 watts? Well, we run this thing 8 hours a day, 5 days a week, and we've been doing it on those same tubes for the better part of 2 years. So it gets the power tube's ability to produce a full 50 watts, get a little weak. That's normal. Why don't we change them? Because we don't need to. We only ever run it at 20 watts for testing purposes. So until the tubes just actually die at death, there's no practical reason to change them. So we don't. All right. So what's important here is that we've reached the sine wave threshold of its output power. And yet, the RMS reading meter is saying that more power is coming out of it than the 20 watts we were at when it was below the clipping threshold. So let's push it more into the clipping threshold where it's getting more and more square wave.
Squarey.
And now we're getting 18 volts RMS. Okay. 1.8 times 1.8 divided by 8. Now it's 40 watts. What's going on here? The power keeps going up. The problem is the power is not going up because this meter is not reading that square wave activity properly. It's an RMS reading meter. It's reading an AC waveform that is designed to be reading a sine wave form. When the sine wave is no longer a sine wave, the number that you get out of the meter is no longer representative of the actual power that the unit is putting out. It's only representing that some combination of the sine wave power and a whole bunch of extra distortion magically got converted to more power, but it's not more power, and we'll talk about why. In the meantime, let's go back down to the point where it just started clipping. How do we actually get an accurate number of what's going on here? We don't rely on this meter. We look at the scope and rely on the peak-to-peak reading that you can get on a scope that you can't get on a meter. And peak-to-peak means basically the amplitude difference between this point and this point. So this is the peak, this is the other peak, and this line represents that peak, this line represents that peak, and the voltage potential between those two peaks is, oh look, 47 volts as opposed to 16 here. What is it telling us? It's reading the voltage a different way that you can understand what's going on more effectively by reading it this way. Now we keep going up. I could keep going it into more distortion, or I could just simply pile a square wave into it.
Oh, yeah.
Now, what's interesting here is the peak-to-peak voltage on a square wave is about 40 volts. When we switch this back to a sine wave, 45 volts. Let's switch it back to a square wave, 44 volts. Huh? This says the voltage is changing from 15 to 20. So there's a like a 15 to 20. So 5. So that's about a 20% difference. Okay. But this says that there's no difference between the square wave and the sine wave at its point of clipping. So what just happened? What happened is it's a square wave now. So the duration between the peak of the positive peak of the square wave and the negative peak of the square wave is wider. So the RMS function, which is designed to basically give you an average of this potential, taking into consideration this angle, which is, it's not this voltage, it's not this voltage, it's not exactly half. It's somewhere in between. And so this RMS calculation is designed to take this average out this angle. That's what the RMS function is doing. It's translating a sine wave into some measurement that you can use to either evaluate or design an amplifier or anything that uses a waveform. So by going to a square wave, we eliminate the angle and therefore the necessity to average what's happening here and here. So you're just getting the raw potential between the top and the bottom. So that's why you can't trust an RMS reading meter to tell you what's happening in the amplifier when it's distorted. And that's why when you take a Marshall, a 100-watt Marshall, and crank it way into distortion and read it on an RMS meter, it's going to tell you that there is a 40% difference in output between what it's doing clean and what it's doing for fully distorted. It's not that much of a difference. It calculates out differently because you're calculating it improperly using the wrong equipment. How do we know what power is really coming out of there? We know by how much current the amplifier is drawing out of the wall. Current is part of the equation. You would think that if it was putting out twice as much power or 40% more power, you would be drawing 40% more current out of the wall outlet, right?
Clue.
Okay. Let's go back to the sine wave now. I'm going to bring it back down to our testing threshold of 20 watts.
So no clipping.
No clipping.
That's clean power.
And I'm going to switch in the PS100. So now the PS100 is in operate mode. It's been idling this whole time, and we've just been using it in bypass. So the signal coming from the PS2 going to the load has been just passing through. Now, the power station is feeding the load, and the power amplifier in the PS100 is driving the resistor. Now check out what just happened. You probably didn't hear this, I'm going to point it out. This is a regulated programmable power supply, an AC outlet per se that I can program to deliver 120 volts at whatever current that this unit needs to operate. So when I turn off the PS100, which is plugged in here, the current coming out of the wall outlet is 350 milliamps, third of an amp, okay? When the power station is operating, it jumps up to 1.4 amps, almost 1.5 amps. 0.4 amps, 1.5 amps. So it's drawing 1 amp more out of the wall outlet in operate mode than it was in standby. Now, watch that the amp reading as I turn the power up. The current from the wall outlet is increasing up to the point of clipping. Now we're at 26 volts RMS here. We're at 74 volts peak to peak, and we're drawing 2.3 amps out of the wall outlet. So, idling, we're drawing 1.4 amps out of the wall outlet, and at full sine wave power, we're drawing 2.3 roughly. So, what's going on here is a tube amplifier is 50% efficient. So half of the power that comes out of the wall is lost in heat in the transformer and in the tubes. That's just turned into heat. So the remaining difference between the power that went in and the power that comes out is the efficiency rating of the amplifier.
Is that basically every tube amplifier?
Yes. So I'm switching this to the wattage reading, the power reading mode, watts, right here. 220 watts being pulled out of the wall outlet. 220 watts out of the wall outlet, but this is a 100 watt amp. And you're saying that it's running at about 85 watts, just barely clipping. So where are the other 120 watts going? They're just radiating off of here as heat. They're radiating off the load resistor as heat. And I don't know if you noticed earlier, but we were at about 105, 110 degrees on the load resistor, and now we're at 195. So we've almost increased the temperature output of the load resistor another 100 degrees. That's where that extra 100 and some odd 120 watts is going. So we can go push it a little farther into clipping. And look, we're not really getting that much more power output. Okay, so now let's go to square wave. Now when we were up here on sine wave, we were at 74 volts peak to peak sine. We go to square. Well, look at that. 72 volts peak to peak square.
Interesting.
The output voltage didn't increase. Only the shape of the waveform increased. It's on for a longer duration because the angles of the side of the sine wave are no longer angles, and they don't contribute to the average, which is what turns it into RMS power. So this meter is no longer valid. It's saying 33 volts RMS, which translates to 140 watts. So just like the Marshall amplifier that puts out 140 watts when you crank it,
The 100
full
watt
right-hand
Marshall.
sweep, what you're doing is you're cranking it into full square wave power
Right.
and reading it on a true RMS reading meter that's telling you that's 140 watts, but it's not 140 watts. And that's where Henning got it wrong when he said 140 or 170 or whatever the number was, sine wave watts. It wasn't sine wave watts. It's not even square wave watts because the meter is not reading the actual reality of what's going on with the power output. The way to know is to calculate the efficiency against the current that's coming out of the wall. So here we have now 288 watts coming out of the wall outlet. If the amplifier is 50% efficient, it's drawing half of the power that's coming out of the wall outlet is being turned into power, but it's not really being turned into power because it's also being turned into more heat. So it's dissipating more heat. There's more heat coming off the transformer, there's more heat coming off the tubes, and there's more heat being delivered to the load, which is being radiated as heat. And that, if it's being turned into heat, it's not being turned into a sound. So even though it says it's drawing 280 watts, and you go, well, if it's 50% efficient, that's 140 watts. Well, no, you're not hearing 140 watts because more of it is being dissipated as heat. The only real power difference there is maybe it's 120 or 130, but it's still distorted watts. It's not clean. So it's not sine wave power. Now let's look at the current that is being pulled out of the wall. 2.8 amps at full square wave as opposed to 2.3 at sine wave. That's a 20% difference in current coming out of the wall, but apparently a 40% difference in power output. How is that possible? It's only possible because of waste and inefficiency and improperly measuring what's going on with the wrong tools. So, why are we going through this whole exercise? We're doing this because why did Henning start talking about it? Why does anybody talk about this? They talk about it because I don't want to use an attenuator of my amp because it's going to blow up my amp. This has been going on since the 70s. This has been going on since the Schultz power soak came out. And every attenuator that's come out since then, this has been the discussion, and manufacturers have reacted to this as well. When the Schultz power soak came out and people started blowing up their amps, they blamed it on the power soak. And Marshall reacted, okay, don't do that. And they started refusing to warranty amps that were used with an attenuator when they blew up using an attenuator. And that caused people to go, Marshall won't warranty my amp because I use it with an attenuator, so don't use an attenuator, it will destroy your amp. All of that is wrong. That is out of context, taking information, mixing it together into a stew, and then spewing it out and saying, this is the result, without any scientific basis or context. All right? So what is really happening? Let's go back to the efficiency discussion. You say that half of the power that comes out of the wall outlet that goes into one of these things, a power station 100 or a Marshall 100 or anything that's 100 or 50 or whatever power rating it is wasted as heat. Yes, that's what I say, because that's exactly what's happening. And how does that translate into blowing up my amp? What we have to do is separate in each instance what is happening when an amplifier fails, because they're not all failing for the same reason.
Because we're kind of talking about three things, right?
Right.
Power transfer output transformer, and tubes, right? Those are the things that are really going to fail.
Right. And those are the things that traditionally failed over time, whether or not you use an attenuator. And so, the older Marshalls, they sounded really good, but they weren't as reliable. And that's all mishmash of information that's been ground together like rocks over history, turning it into this unintelligible dust. Okay. Why was a Marshall amplifier unreliable on the road? Well, did they make it to be unreliable? Probably not. So what happened when it went from the factory to the touring musicians' hands? They transported them in whatever vehicles they threw them around in. They rammed their guitars into them and knocked them over. They plugged in and unplugged the impedance selectors to different impedance selections depending on which cabs were being used. They tripped over the cables. They poured drinks in the top. They put power tubes that were kind of failing or on the verge of failing, and then they blew a fuse, and then you replace the fuse with tin foil to get the amp to just play one more song before smoke started coming out of it, and on and on and on. It still all boils down to sort of three basic areas that cause amplifiers to fail. First one is the power transformer. It's part of the power supply. This is the part of the amplifier that does 80% of the work. It's also the part where 80% of the power waste occurs. I can barely put my hand on this because we've been cranking the hell out of it. So it's a big block of steel. And as it does its job converting one kind of power into another kind of power to run the tubes, which the tubes then use to run the output transformer, which is then converted to a voltage at an impedance that the speakers like, it's doing its job all the time, regardless of whether the tubes are working, whether they're on standby, or whether there's sound going through the output transformer. The power transformer is always working. It's always generating heat. And as it generates heat, the core gets saturated with heat. And the more you drive it, the more the heat builds up inside the transformer. Now, while I've been talking about this, we've been running power into our load resistor. And if you listen, you can hear when I turn to operate mode, you can hear something winding up a little bit like an airplane engine.
It totally does.
Engine. That's the power supply protecting itself. Its fan is sensing more current getting pulled out of it, so the fan speed is gradually increasing because it's dissipating more heat. Over here, this resistor that was at about 170 degrees or less when we first started our conversation is now approaching 300 degrees. There's no fan on it. It's absorbed all the heat that it can absorb without some help. And by help, we mean a fan. Because in order for a resistor to continually absorb heat up to its rated amount of power, it has to have a way to extract that heat out of it so that it can absorb more heat, more energy, convert it to more heat. And that's the thing about load resistors and speakers and every other kind of load, is that their ratings are expressed nominally. That means under normal conditions, whatever those are, this device will dissipate this much power until it can't do it anymore, until it gets saturated with power. And then you have to do something to it to make it be able to handle more power. That means you have to take power away from it. This is heat exchange. You have to take the hot air out, the hot element out, and replace it with a cold element. You do that by putting a fan on it. You do that by mounting it on a heat sink. You do all these things to help that resistor convert more energy into heat. So now I'm going to draw your attention back to the meter that shows the temperature, and now it's dropped about 40 degrees. Just because I turned the fan on. I still don't have an aluminum heatsink on that thing yet. If I did, it would probably drop down another 50 to as many as 100 degrees, because that heat would fan out over the aluminum structure, and then the air in the room would help exchange the hot air on the plate to the cold air in the room. That's called heat exchange. Okay, now going back to the efficiency and the heat of the components. Just like the resistor, the transformer core gets saturated, and in order for it to continue generating power, it needs to be cooled, and that's why there's a fan in here. This fan is mounting on top of a heatsink assembly that has the resistors that are absorbing the heat from the load you put into it. But it's a much bigger fan than is needed to do just that job. It's also sucking in some of the air around the transformer, and it's sucking in some of the air around the tubes and blowing that all out the top. There's vents on the bottom, there's vents on the top, there's vents under the tubes, so there's plenty of room for convection for the colder air underneath to circulate through the unit and get pushed out the top. And all the fan is doing is to help that process. So as long as we keep the temperature of the power transformer under control, it will continue to do its job for hours and hours and hours. In a typical amplifier head, you don't have a fan. You don't have vents underneath it. So, and it's usually bigger. So that big mass of steel and copper gets saturated more and more. The temperature gets progressively hotter and hotter while it's doing that job. So the big brunt of the activity is here, but we also have the power tubes, which in any amplifier where the head is sitting on top of the cabinet, the big killer of the tubes is vibration. The speakers are vibrating, causing the cabinet to vibrate, causing the amplifier on top of it to vibrate, causing the tubes to vibrate. It's the vibration that kills the tubes. Rolling your amplifier with the head on top of it on casters across the street with a real rough concrete surface, you're basically just shortening the life of the tubes. So all of that vibration is loosening up the components inside the tube and making them more likely to fail at some point. So if you're touring, you're exponentially increasing the amount of vibration damage that the tubes will see. So that's a bigger part of why tubes fail than them just processing power. And then finally, there's the output transformer. The output transformer, if I put my hand on this transformer and try to hold it down, I can't really hold it there very long. It's probably about 150 degrees right now. There are some spots on the tube I'm not going to touch. They're as much as 250 degrees on specific parts of the tube. The output transformer, no sweat. I can keep this crank for a while for the rest of our discussion. We're running at 200 degrees off of the load resistor, but I can keep my hand right on the output transformer. It's not getting very hot. Why? Because it's not converting too much power. It's not doing the job that the power transformer is. It's doing a different job. It's just converting the impedance of the tubes to the impedance of the speakers. So it's not wasting very much power in that process. So we've got three different components that when I blew my amp and it sounded great just as I was playing that last solo, three possible different dynamics are going on. Whether you used an attenuator or not, the power transformer is getting hot. And if you play a 4-hour gig at full volume on the amplifier, it could potentially get hot enough to fail. If you're doing that for 4 hours with the head on top of two 412 cabs or even one 412 cab and banging it away for 4 hours, the tube vibration, which is continuous, driven by the heat, which makes the mechanical parts inside the tube more flexible and more susceptible to vibration, can break down. So the tubes could short out, and that would be the cause of blowing a fuse. So you have, most big amps have two kinds of fuses. They have an AC fuse and a DC fuse. If the AC fuse blows, it's usually because the power transformer failed first. If the DC fuse blows, it's probably because the tubes failed first. But if the output transformer fails without the tube failing, what would cause that? That could be caused by a bad power cable, a bad connection on the impedance selector. It could be caused by just running it so long, and the transformer, if it's a vintage amp, 50-year-old, 60-year-old amp, and you're pounding the output enough for it to get hot, it's going to be expanding and contracting. And older transformers like that, they are insulated the same way new amplifiers, new transformers are, with a layer of varnish on each coil of wire. The wire itself has a varnish insulator on it. So if two wires are laying on top of each other, there's two layers of varnish separating those two wires. And over time, as those wires expand and contract and move like this relative to each other, it sands down that varnish to the point where if you do it long enough, you can break down the insulation between the two. Now, unlike a power transformer, which gets so hot that it actually melts the varnish inside and causes a hard short on either the primary or the secondary, that would blow the fuse, and that's the most likely part that's going to fail because of playing it a really long time. But if you blow the output transformer in that process, usually something went along with it, like a bad connection on the impedance selector, a bad connection between the speaker cable connected to the amp or connected to the cab, or if you blew a speaker, that could cause a voltage spike that could arc the tube or the transformer. So output transformers usually don't die because of heat. They usually die because they got arced. What do we mean by arced? Again, they have the same two wires laying on top of each other, and layers and layers and layers of these wires laying on top of each other. If a tube should short, it will cause a big voltage spike that's big enough to jump from one wire to the other through that insulation. If that happens on the primary, you'll blow a DC fuse. But what actually happened? What happened is a voltage jumped from one wire to the other wire through that insulation. And if you open up the transformer and find where that short occurred, you practically have to have a microscope to see the short, because it'll be a tiny, tiny, tiny pinhole. If you take a straight pin, not the head of the pin, but the tip of the pin, it's a little more than the diameter of a pin at its sharpest point. That would be the diameter of the carbon connection between those two wires.
That's insane.
That's all it takes to blow the transformer. If that arc occurs on the secondary side, you'll hear the volume drop way down, like as if you put it through an attenuator and turn it all the way down to zero. So if the DC fuse is blowing, it's either blowing because the tube failed or the output transformer failed on the primary. If the volume suddenly goes down to nothing, either a tube failed or the secondary of the transformer shorted, and it's just basically shorting the out, like a shorted output. That shorts the whole signal to ground. You'll hear it buzzing inside the amp. We did a video talking about my amp has got ghosts in it, because when you attenuate an amp, you can hear the amp vibrating. Same kind of thing. You would hear the amp sounds like it's raging away inside, but there's no sound coming out of it. That's the output transformer failing. So in all the stories that you hear about how much power it really puts out, or what caused the amp to smoke when you were just playing the most righteous solo you've ever played in your life, it's usually going to be one of 3 or 4 different things, and they're usually not necessarily related to each other. How does that manifest itself when you're using a attenuator? All you're doing when you use an attenuator is you're giving yourself permission to beat the crap out of the amp all the time without damaging your own hearing. That's all you're doing. You're allowing the amplifier to be operated at its maximum limits for longer than it would normally survive, or you would survive if you were doing that into a cab. You'll probably blow the speakers in the cab after 4 hours of that, or even 2 hours, or even 1 hour, depending on the age of the speakers and the power rating of the speakers. You never know. But the attenuator doesn't cause the problem. The attenuator exacerbates the problem because it gave you permission to basically hijack the performance of the amplifier so that you could get out of it what you wanted to get out of. It's just like if you're driving a car up a steep hill, a car that's in good condition, that's had regular oil changes, and the cooling system is in good condition, and you floor it and you go up a really steep incline for an hour, it'll be fine. If you've got a pinhole leak in your radiator, or you haven't changed the oil in 2 years, or the oil level is low, or you have a leaky gasket or a bad oil pump, and you try to do that, one of those things is going to give up, and the car is going to fail, and you're going to say that hill killed my car. And then that will be not true. What will be true is you didn't do the maintenance on the car, you abused it, you knew that it wasn't in good enough condition to go up that incline, and you did it anyway because it was fun, and who could blame you? This is the kind of misinformation that causes manufacturers to say, I'm not going to warranty our amplifiers if you use them with attenuators, because that's completely sidestepping the whole issue. I understand that you have to have some kind of warranty statement in an owner's manual that indicates that certain kinds of abuse of the equipment that aren't directly the cause of the equipment might not be covered under warranty if you use that equipment with other equipment that allows you to beat the crap out of it. I understand that. I feel like personally, we spend a lot of time designing output transformers and power transformers so they can take all kinds of abuse, and we're designing and building a product that is designed to inflict pain on your gear, and we do produce the kind of gear that's meant to be plugged into a piece of equipment like this to be abused, and we understand all of that, and so we design our products accordingly. And that's why we don't think there are attenuators out there that could just in and of itself plugging that device into the amplifier will cause it to blow. That's why we feel confident that we don't have to have this warranty disclaimer that if you used an attenuator, you're screwed. If you use an attenuator and you didn't maintain the amp and it's a couple of years old and it's still got the original tubes and one of them is shorting out, we'll find that out. If you, for example, sent it to us to check out, we would say, yeah, this likely happened. You would see evidence of that. Just using an attenuator with the amp by itself, all other things being normal and well maintained or properly designed and built or in good working condition, that's not the reason an amplifier would fail using with an attenuator. So what we have covered now is what sine wave power is, sine wave power, RMS power, clean power, relative to square wave power, maximum balls to the walls, full right hand sweep power. These are all different ways of stating how the amplifier circuit behaves under normal conditions, extra normal conditions, completely abnormal conditions. And trying to put a number on that, like 170 sine wave watts, is kind of irrelevant. It doesn't really describe what's happening or what could happen to your gear because of that, or how much more likely an older Marshall with higher plate voltage is going to be to blow or damage an attenuator than a later one that had lower plate voltage. These are just like degrees of behavior and use cases. They're not this one makes or this one breaks the gear. Companies that make loads and attenuators rate them different ways. We rate ours at 200 watts on the load, and because ours has a tube power amp in it, people often conflate the output power of the power amp section to the input power of the load section. So the PS2 is a 50 watt amp, the PS100 is a 100 watt amp, but both of their reactive loads are 150 to 200 watts, continuous RMS power at whatever impedance you have it set at. So 2, 4, and 16 ohm, 200 watts, 8 ohms, 150 watts. That's the amount of power that the reactive load can take continuously, as long as the fan is running and as long as you've got reasonable ventilation around the unit. If it's in a hot room, or if you're in an environment where the operating temperature is going to be higher than usual, like in a rack system where you're really pounding it. People ask us all the time, do I need to put an extra rack space above or below my power station in my rack system? It depends on how you're using it. If you're in your man cave and you're not like really cranking your amp very hard, you're just using it to bring it down to a sane level or a comfortable level or a very, very low level, but the amp, it's a 30 watt amp, a 40 watt amp, a 50 watt amp, and you're slamming it about a medium amount of power output, no, you don't need an extra amount of space for ventilation, and it isn't going to generate enough heat to damage the gear above it or below it. However, if you're taking a 100 watt amp and doing a full right hand sweep and playing it like that for 4 hours, for sure you're going to need extra ventilation, and there's also a very good likelihood that you might blow the power transformer if you're not careful. You would have to make sure that your amplifier is well maintained when you do that, and you really would need to take a break once in a while and not do that continuously for 4 hours unless you're playing a concert and you use that kind of gear and you run it that hard, that often, day after day after day. And if you're doing that, then you're bringing extra gear and you're maintaining it and you're paying somebody to take care of it and you're doing all those other things that go along with that. But if you're just doing it at home, it's simple enough to take a break and let everything cool down, because as I said before, the core of these components accumulate heat and it needs to be evacuated after a certain amount of time. And once you do that, you should be smooth sailing regardless of what kind of attenuator you're using and regardless of how loud the amplifier is. So Henning, totally cool. Just be careful when somebody tells you a number. I know you don't really know this stuff inside and out, and I know that it isn't really that important, and I know that you won't spend this much time describing or explaining it because it's difficult to describe and explain, and it's not really your job anyway. So thanks to the posters and the people that emailed us and commented on our videos that they would like us to weigh in on this, and happy to do it. And I hope that you found this so boring that you just now want to get on the bus or take an Uber to the nearest bar and get yourself a really nice margarita. So have a great weekend. Thanks for sticking around for this. I don't even know what it is anymore. I've lost my mind. Have a great one. Take care.